Swayam Prabha. Digital India. Educated India.
So let's now change gears and look at the attributes of networks which are used for high performance computing. Again, we will start with the same slide that we saw earlier. Uh, the basic way in which you can represent a parallel computer is like this. And I had also told you last week that we have something called as multiple instruction, multiple data kind of computing system, wherein you have now we don't confuse this execution unit with the execution unit inside the processor. So this is a generic term that is used because you may have it on a inside a single CPU, or you may have it as a two different processors on a same motherboard, or it could be two different CPUs which are connected by a network. What is more important to know here is that word multiple instruction and multiple data. That is, each CPU has its own instruction, and that instruction I mean it's independent of other processor, and there are independent data streams. So here you will find that I1 is operating on D1 and I2 is operating on D2. So now we have shown instruction as coming from the same memory and D1 and D2 coming from the same memory. In one instance, it could be like this, and in some cases, which I shall describe in the slides to come, they may be disjoint in the sense that they may not be connected to each other. What is more important is there are two execution units. Each one of them has got an independent instruction, and each one of them has got an independent data. Okay, so that is why that multiple instruction, multiple data is that key word there, key phrase, and its manifestation can come in various forms. And most of the parallel computers that we use today are of this type. They are of MIMD type. And as another thing I had told you last week was SIMD, single instruction, multiple data. So that comes, if you remember, I had told you that that is also there, but it comes in the form of an instruction, a vector instruction inside the execution unit. Okay. But at the architectural level or at a gross level, you can say most of the high performance computing systems are of type multiple instruction, multiple data. Having said that, as I mentioned, the manifestation can come in various forms. Two of them I've mentioned here. One of them is called as shared memory, and other is called as distributed memory. So these are the names that are given to the architecture. So there is a reason for that. As the name suggests, it will be evident to you in the slides to come. So this MIMD, as I said, there are of two varieties. One is the shared memory. So the processing elements, they will share a set of memory locations. So because they are sharing and all the processors are connected to that shared memory, we will call it as tightly coupled, because the processors are on the same board or at the same physical location inside one box, and they are having a common memory. Other one is as an opposite of shared, that is distributed, meaning each processor has got its own memory. As a result, they are loosely coupled. They are not tightly coupled, because in this case, the shared memory is the common thing that binds them together. Whereas because the memory itself is distributed, each processor is having its own memory, they have some mechanism to connect, and that is a loosely coupled architecture. Okay. And in shared memory, there is what is called as symmetric multiprocessing, that is SMP, and other is called as non-uniform. So symmetric means all processor can access in a uh, uh, equally what I would say in an equal rightful manner, if I may use that word. When I say rightful, equally rightful means that all of them have got equal rights over that shared memory. All of them will have the same access times. Of course, not we have to be aware of the fact that if two processors are accessing the same memory location, obviously one has to wait. But if the accesses are independent of each other, then they will take the same time. All of them are connected in the same manner to the memory, so it's symmetric. There is one implementation, I will show you the diagram, where the access is non-uniform, meaning some memory locations are fast, access to some memory locations are fast, and access to some memory locations are slow. So why it is non-uniform, why some memory is fast, some memory is slow? We will call it as local memory and remote memory. If the memory address is local, close to it, it is fast. If it's remote, means belongs to some other processor, then it is slow. Here, every memory is local memory. All of them are connected to the same memory. Hence, it is symmetric in nature. Every memory location is as fast as possible accessible. Again, remember, two locations accessing the same memory location, weight has to come into picture. But here, the diagram will help you in understanding why we call it as non-uniform. Okay, so that is about the shared memory. Whereas in distributed memory, the nodes are connected in a form of a cluster. I will explain what that cluster is in a time to come. First, let's look at the SMP architecture. So it's a standalone computer, a box. Okay, it will be a box that you will see a server having following characteristic, and two or more processors with comparable compute power, means let us take a box having two Xeon processor, each running at 2.5 gigahertz. Okay, so that comparable meaning that it is not that one is slow, other is fast. That is not the case. They will be typically having, let's say, two processor, four processor. Systems have been designed with 64 processors in the past. I think the name was HP used to make something called as Superdome. So you could have up to 64 processors in them. What is important is all processors share the same memory, which I have made much emphasis on in the previous slide, and the IO facilities, meaning if one processor wants to read from a network, it can do that. Another processor wants to do it, that also can do it. So there is nothing that is different from each of the processor. Everything is same for all the processors. The same memory, the same IO, and they are all equally accessible to all the processors. How are then the processors interconnected? Okay, a common way of connecting them is a bus. I will show that in the diagram in the next slide, or some interconnection scheme. Some use what is called as a switching matrix or anything, something which allows them to talk to each other. That is more important. Okay. Now that symmetric word has a significance that the access time for all processor is almost. We say almost because sometimes it could be slower because of the queue that the access may get into. All the processors have can access all the IO devices, so that symmetric is being emphasized again and again, and all processors can perform the same function. That means if a thread is to be scheduled, any processor can take it. There is no such thing like, oh, this processor is fast, so let's put it there, or this processor can only access the hard disk, so put it there. Nothing like that. All are have equal rights to all the resources, including memory and IO. Okay, and such a computer is controlled by a single operating system. Okay, that allows assignment of processors to programs or processes or task or thread. Anything has to be run on this system. The single image of the OS handles it. Okay, so this is important, that and diagram should help you in understanding. So there is a shared bus here, okay, on which all the interconnection is happening. So this is that important bus on which this processor has. Now this cache is its private memory. So that messy protocol that I told you is applicable to such a system, that there is a private cache and there is a shared main memory. So we had said that if processor 1 reads a variable, and if it just reads it, then any other processor can also read it and keep it in their cache. But moment it modifies it, one processor modifies it, others are supposed to take cognizance of it because they have a shared copy of that variable, of that particular variable. So those things will come into picture, but for the sake of discussion of what we are talking about now, what is important is this main memory. Any processor can equally access it. Any processor can also access the all the IO devices that are present, like disk, network, CD-ROM, anything that is present here through this shared bus, it can access. Okay. So that is how SMP's architecture can be generalized. Okay. So what are the advantages? Why one tries to use an SMP processor, SMP kind of motherboard? There are a couple of advantages here. Availability. Like in the previous example, if a new process has to start, the main memory will see which processor is loaded least. On that, it will schedule that process. Suppose processor 1 fails and OS gets to know about it. What it will do, it will anyway those processes that here where will be lost. The user may start them again. But if new processes start, it will not schedule it here, but it will schedule it in the remaining. So if there are 16 processors and one fails for some reason, the system will continue to function. Of course, something will be lost because what was running on processor number 1 is definitely going to be lost, but others can continue, and those processes which were lost can be relaunched on the remaining processor. Newer processes that come in, they will be not be scheduled on processor 1 but on 2 through n. So that is the availability part. Incremental growth, like the architecture is such that the user has less money today, he may take a 4 processor system, he may add 4 more processor. The OS knows that there are 4 more processors, so it will schedule now 8 processes at a time. So incremental growth can be done based on the budget. And scaling means the system is designed such that let's say HP designed Superdome, they will offer one version with 8 processor, another version with 16 processor, third version with 24 processor, something like that, to make them affordable, to give higher performance at higher price. So all that is from the vendor's perspective. That's the reason SMP systems are useful in such situations. So that is SMP. Next is the non-uniform memory access. Let's see how it looks like. So to understand NUMA, first we need to understand what is UMA. So all processors have access to all parts of the memory. We saw that in the previous diagram. Access time for all processor means all the memory locations are equally far away from the processors, all the processor, and the access time is same. Example of UMA is SMP. So all these attributes we just saw, they are applicable to SMP. So now let's see the difference. What is a non-uniform memory access? Now the important part is first statement is same, that all processors have access to all the memory that is present, all of the main memory. But there comes a difference, that the access time for a processor is not uniform, which is what we said in the for UMA. How does it differ? It differs based on which part of the memory is accessed. So broadly, you can say that for every processor, there is one region which is fast, which we will see is the local memory, and there is one region which is slow, because it's a remote memory. It is with some other processor or somewhere else, and this is true for all processor. So every processor will have a fast local memory and a slow remote memory. Okay. So this is how it looks like, non-uniform memory access. So if processor 1, if processor 1 wants to access this memory, then it is going to be fast. Why? Because this memory is local to it. There is a direct connection between this. But suppose this processor wants to access the memory which is local to another processor, then first he has to make sure that he has to get access to the bus. No other processor should be using the bus. Once he gets that, he has to put the request here. But this memory is owned by this processor. So this processor has to grant access to processor 1 to access a memory which is local to it. Because it has to make sure that while P1 is accessing M2, P2 is not accessing it. So a write has to be obtained by P1 to access M2. Hence, you would notice that accessing M2 is not as fast as accessing M1 for P1. Thus comes the name non-uniform memory access. But remember, the addresses are contiguous in many cases, like let's say it will begin with 0 to, let's say 1 MB is here. So 1 MB plus 1, rather 1 to 1 MB is here. 1 MB plus 1 to 2 MB is here, and 3 MB to 4 MB is here. So when the processor wants to access 0 to 1 MB, it will be a local, but beyond that it will be remote. So like this, the memory access time varies whether the memory to be accessed is local or remote. Okay. But why do we go for this complex architecture? Why can't we keep adding more and more SMP nodes? The reason is as follows. SMP has practical limit, like I mentioned to you, 64. So that is something that HP thought that beyond that it will become really huge and complex. Not only the hardware part becomes complex, the OS also becomes complex. So mechanical, electrical, PCB design constraints, they all come into picture. Okay. So as I mentioned, 64 is typical. I mean, nothing prevents anybody from designing a 128 processor system, but it will be very, very expensive, and then won't be affordable. And if it's not affordable, if it doesn't sell, then obviously they will lose money. So they may not make it. NUMA offers same advantages as SMP, like flat memory. I showed you 0 to 1 MB in memory of 1 to 2 MB in second, 2 to 3 in the memory of third. So, and other is single OS image. You don't need multiple OS images as in case of cluster, which I shall explain later, but it's a single OS image. But the physical restriction, see, we saw 64 is the restriction for SMP. There is also a physical restriction to NUMA as well. It may be extend to hundreds to thousands of physical cores of processor, like Altix 8400 of Silicon Graphics can have 64K cores. Okay, this is not processors, but it is cores. But they are all in NUMA architecture, meaning some processor will have faster access to some of the memory location, and the same processors will have slower access, which is private memory, to another adjoining processor. Okay. So I hope you understood the difference between the two. So here is an example of NUMA. So if you notice here, this is a motherboard, Intel motherboard with two CPU, two socket motherboard. So now here, if you notice here, this is so this is node 0, which has got 4 cores. They have their private memory. This is node 1, which has its own private memory, but the addresses will be from, let's say, 0. If there is if you notice here, physically it is connected like this, that the CPU has a memory controller. We had discussed this last week also. I had answered one question where we had said that the memory controller is integrated into CPU. Okay. So the memory is connected here. This is another CPU, CPU 1, 2, 3, 4. The IO is common, and each one of them has a dedicated path to another CPU. Okay. So thus this is that high bandwidth dedicated path. So if this, let's say suppose the total memory is 4 GB. Okay. So out of this 2 GB, first 2 GB will be here, next 2 GB will be here, and this CPU will try to access first 2 GB, but if it wants to access the next 2 GB, it will go through this socket interconnection, go to the next processor and ask him to give access to the memory location which is private to CPU 2. So here it shows one diagram which has got 4 CPUs. Okay, so you get motherboards with 4 CPUs. So that is a non-uniform memory access. So any questions about these two, SMP and NUMA? All right.
Sir,
Yeah. Yeah.
there's one question.
Yeah. Go ahead.
So in the SMP system, each processor is symmetric, right? But
Symmetric in the sense access time to memory location, irrespective of what it is accessing, is same.
okay, okay. So there's no restriction that the processor must be symmetric or all the processors must be same.
So see, it is like this. The architect, the way they are interconnected, the way the processors are interconnected with the memory, that scheme is called as being symmetric.
Hmm.
Okay, so there is no concept of remote memory and local memory. There is only one memory. Of course, there can be cache where a local copy of the variable can be stored, in which case the MESI protocol needs to be implemented.
Okay.
Whereas in case
Okay.
of non-uniform memory access, uh, the I mean, though you can have one common memory, but in the implementation that I showed, all the memory that is present is connected to a processor, one processor. So if the processor uh, was to uh, was to access or operate from its private memory only, then if each of the processors are operating from their respective private memories, it will be very fast. But the moment they want to access something which is going to be likely to be the case, something from the memory that is connected to another processor, then a dedicated path exists and they will get the data from there. So that possibility exists, but the speed is going to be less if you access remote memory. Such a concept does not exist in case of SMP. SMP, all
Hmm.
the memory is common and it is at equal time distance from all the processors.
Okay. No, my question was it was like so in modern SoCs, systems on chips, would you call these SoCs with, for example, ARM's big little cores? Would these be NUMA or would those be SMP?
Uh, uh, can you tell again which processor are you referring to? I am sorry, I didn't get it.
SoC, a system on chip, for example,
Right,
these
right. No,
qual.
no, right. So system on chip is again, again it depends upon like you can say that this part is system on chip, this blue one. Okay, can you see this node 0?
Yes.
So this is a system on chip and it is SMP in itself.
Okay.
Okay, but today you also like ARM, particularly ARM, you get inside the same processor, you may get something like this, that there are multiple cores and each core having its private memory. And that core is internally it may have, I mean, they use all kind of things like chiplets, and uh, it all depends upon the nomenclature that you are using. So what will happen is you can say a node is an SMP, okay, and that every SMP node has its private memory, and within that node, all the cores are SMP in nature because they can access any of the internal memory. However, there also exists one more bus on which other processors, similar processors are connected, which have their own memory. So on this side, it becomes NUMA, but within this, it becomes SMP. So it's always a hybrid.
Okay. Thank you.
Anybody else has a question about SMP and NUMA? All right. So we will now look at the next architecture, that is the cluster. So the cluster is formed using network. Okay. So network plays a big role in forming clusters, because that is the network is the one that connects the distributed computing systems. So there are some standard topologies in which one can connect these nodes. So some of them are shown here, like IBM. I mean, it's no longer there, but they implemented what is called as token ring. So remember, topology is arrangement of nodes, how the nodes are interconnected. That is what defines that's what is the definition of a topology. Then there is a mesh. So mesh will you will say that to reach from a certain from A to B, it can traverse to three paths. There is a direct connection and there is an indirect connection. So not every two nodes will have redundant path, like this one does not have a redundant path. As a result, if from here to here, if you wish to go, then there is only one path that one can take, which is the shortest path. But if you really want, then you can also go through other paths. So that all depends. There is a science which deals with the topologies and the algorithms that route this data across such networks. And it is more prevalent in telecom networks, because you need to involve some kind of redundancy in the network. So that is a mesh network. Star, as the name suggests, there is one central element which is the key element, and all the elements are connected to it. Okay. Fully connected means each one of them is independent in nature, but each one of them is connected to each remaining n minus 1. So that is fully connected. So each one, this one has got its own disadvantages. Like if you want to add a node, you have to make n minus 1 links to remaining nodes, so which may not be possible, because the number of links available in each of these nodes can be limited. So there are ways and means of overcoming that. And the ring, if you open it, it becomes a line, obviously, so that loop back is closed. So to reach a particular node from any other node, you have one path only. Tree, this is like the data structure tree you would have studied. There are always a left and right for every node, and then you can traverse using the principles of node traversal. And bus, no longer in use. A common bus like Ethernet, originally when it was designed, it used to use a bus architecture. Okay, that's no longer in use, because any fault anywhere on the bus brings down the whole network. So that is, in that sense, star is preferred, because if a node goes, only that node will be affected. So that is the basic ways in which the topology decides how the arrangement of nodes is going to be. So to connect them, you need some devices. Okay. So a hub. So I'm sure all of you know that in networking you have certain layers: physical, data link, network, transport, session, presentation, and application. Okay. So at every level, at the lower 3 or 4 levels, there are devices that bridge the traffic. So hub is nothing but an amplifier. It just takes the signal and broadcasts it to remaining other ports. So this is the most primitive one, and it operates at the physical layer, because it is simply magnifying or amplifying the electrical signals, because they may get degraded. So you need to magnify them, so that more than magnify, you are repeating them, and if the synchronization is lost, you will add it. So this operates at physical layer, the hub. You go one level above, which can bridge two networks. Okay, so there is a data link layer. So this is used to connect networks, because the bridge is operating at the a layer which is above the physical layer. Okay, so it will only connect. It will just forward the frames based on what is the destination address. Whereas a switch is something that goes one level above. Okay, and it is similar to a bridge, but it is multi-port. Bridge is typically having two ports, as the name suggests, it is bridging two networks. But it also has other features like buffering. So incoming packet is first in the buffer. If there are any errors, the project packet is rejected then and there. But if it's good, then it will be forwarded further. Okay, so it's basically a switch is like a multi-port bridge. So no difference in bridge and switch in that sense. The router is something which operates at one level above, which is a network layer. Since it's operating at network layer, it is connecting two networks. So what is a network? A network will have an address. Like suppose, let's say this is one network with nodes here. There is another network with nodes here. And you connect an Ethernet bridge in between. So it knows what nodes are here, what nodes are here, and based on whichever nodes are here or if the packet is broadcast, then that data is sent onto the other network. Okay, so this is what that switch is. So switch is having multiple bridge port, and it has got buffers. So the packet that comes in is completely taken in. It is checked for if there is any error. If it's not there, then it will send it on the output link. And these are the additional feature that a switch has, which bridge does not have. Okay, so and the router, now this is so this bridge, this is operating at data link layer, meaning it understands, this bridge understands the MAC addresses, medium access control address. Some of you would know that there is a 48-bit Ethernet address. So based on that, it forwards the packet. Whereas a router will connect to networks. So like 192.168.1.1 and 192.168.1.2. So if two networks are connected, then it is called as a router. So anyway, those are the basic things. Just I'm sure either it was covered last time, like in the last week, or you already have an idea about it. Okay. So now comes the cluster. So a cluster is a group of interconnected standalone commodity computers which together can act as a unified compute resource. A crude example of this is in your lab, let's say there are 30 desktop Linux machines which are connected over Ethernet network. They fall into the category of compute. They fall into the category of a cluster. So cluster is an certain number of devices in terms of compute nodes which are connected together using a single switch. It could be 100 Mbps Ethernet, it could be gigabit Ethernet, it could be 10 gig Ethernet, any of this with a switch and having all those advanced features like every packet coming in is monitored, it is verified and then put on the output port. That is all done here. Okay, so that is what a cluster looks like. So you take, now remember that commodity computers, meaning your desktop or low-end servers, they will serve the purpose. So what are the benefits of cluster? Okay, first is extreme scalability. So you just keep adding the switches and the bridges and you can have thousands of machines, each one of them being even an SMP. So that is how you work. So all the processors will share a network interface card. Other advantage is incremental scalability, meaning you can keep start with 10 node cluster today, add 20 more nodes, make it 30, then add 10 more, make it 40. That is how it works. It also has high availability, which means if a node fails, that process will get terminated, but remaining nodes will have the ability to run the code. Please remember that part what I said earlier, that it's standalone commodity. That means you can simply go to the market and buy that computer or a server. Make use of them. So because they are commodities, they are slightly cheaper. Okay, they are not top of the line. They don't give best performance, but by putting them together, you will get good performance. But what is important here is that each of these nodes are much cheaper because they are like commodity nodes. So I hope you have understood what the cluster is. So any questions that you have about cluster, SMP and NUMA? I hope now you are able to
Yes.
understand the difference between them.
So I have a question like this cluster is like we have a high availability. So we are using the uh, star architecture, right? Star, what was that? Next to star architecture.
So it
The
depends.
fully connected architecture, right?
No, see, topology is one part. Okay, it could use any of these methods, but star is preferred one. Star is preferred. Fully connected is not scalable because you add. Let's say now you have in this example that you have six nodes. So every computer has five nodes, five links going out of it because it's connect and every one is connected to n minus one. So if you add a node, each one of them will need a extra link. So fully connected is for very core number of nodes if they are there, like in a telecom switching or something. But in generally in computing clusters, they are of type star. Most of the time they are of type star. Okay, so that is you by making use of a switch. So what is your question?
Okay.
So you see it's
Yes,
here.
sir, I get it.
Yeah, this is a switch. Like
Yes.
I will just show you an example of Param UR2. So that has got 288 node. There are 288 ports on a single switch, and 288 compute nodes are connected to it. Okay.
Yes, sir. So these are connected by a star architecture, right? So that
Yeah.
way they have a high availability.
Yes.
Okay. Okay.
And high
Yes, sir.
availability is in the form that if a node fails, then obviously what was going on that is going to be lost. So anyway, that is an issue, but there are others who can take the load. So that is what that we mean by that, because the software, there is a OS and those clustering software will take care of that. Okay. And finally, because you are using the best, cheapest thing, not the cheapest, but it's available as a commodity, the prices come down. Vis-a-vis, let's say you take a 64 node Superdome, it's going to be really, really costly than 64 individual nodes if you buy. Okay, all right.
Yes. Yes, I got it.
Any other question anybody has? All right. So now here the crux is because the nodes are commodity, they are not high performing. They are like okay kind of thing. Like I mentioned to you that you can look for this concept called Beowulf. I'm spelling may have been wrong. I may not, but it's Beowulf cluster. If you look at it, it uses a standard desktop, Ethernet, and Linux, and you can create a cluster out of it. So it's everything is open source. So and everything is available in your lab. So you can create a Beowulf cluster. However, if you really want to make a good performing HPC system, then the network becomes a vital component. Why? Because that is what is putting all of them together. And any exchange. So now remember that uh, any data is spread out, and if you want to get that data, obviously you will have to use the network. Okay. So this has every application that runs on distributed computing has an communication is a very, very important thing. And tomorrow Preeti will tell you how MPI works. So that will bring out the essence of cluster. Okay. But here I am only going to tell you about the way it is used or what is its significance. So you can set up a relationship. Are some nodes, is there a master node and some are worker nodes, or is it peer to peer? How the data is going to be distributed initially, that it plays a significant role. Like when the program starts, it's like this. In any parallel program, there is going to be one init section, okay, which is typically serial in nature, because that is then there are the parallel threads that will occur on the nodes of the cluster, and there is a close where the results are collected from. So here you distribute, here you collect, and then you reach a conclusion. Okay. So data distribution happens here. So large amount of data is going. Let's say there are 100 nodes. Each one of them will get data from the master. In between, they may need to access the memory of others. So that is during the runtime, they may exchange data. So that's where network comes into picture. And finally, data collection. So scatter, work, gather. So network plays a big role. So computation may halt if it's waiting for data. Data is required from neighboring node, but the network is congested. Data is not coming. Means network can play a significant role in overall execution of perform. Okay. So if the cluster is large and if the data is not coming at the time the computing wants, then there is an imbalance between compute and communication. And one of the aim of a good algorithm for cluster is overlapping computing with communication. Like it will be, if you look at any node, if you look at what's happening on that, there is a computing, uh, I'll call it CP, and then COM. CP, COM. It's like this, that it keeps happening on any node. So whatever is required here, can you communicate and get it in advance so that CP can go ahead? While this CP is going on, can the compute, that is this communication, can it happen while this compute is going on and get the data? So that is one of the things that a good algorithm tries to achieve. Anyway, we don't have time to go into that, but Preeti tomorrow will give you some idea about how MPI codes are written, and that should give you the significance of network will be brought out to you. So there are two main attributes of any network, whether it is a network for LAN or WAN, or this network is typically called as a system area network, what we use in for HPC. So bandwidth or throughput also. So there's an amount of data transferred in a second. So this depends upon the raw data at the physical layer. So if a 100 GB network is running at 100 gigabits per second, another network is running at 10 gigabits per second. So the first one is 10 times as faster as the second one. Then comes the latency. So latency involves like you have data in memory of one computer. Then the packet is scheduled. Packet goes on the network. It reaches the memory of the second computer. So from the time the packet is scheduled on first one till it is delivered to the second, we will say that is the latency. Okay. So it is useful, that latency, in the sense that lower the latency. If the latency is low, that is the attribute. Bandwidth should be high, latency should be low. I'm sure that you already would have figured out. So lower latency is useful for lots of small messages, because there are some lots of small messages which are traveling in the system. They are more concerned about latency and less concerned about the bandwidth. Okay, because their size itself is small, so bandwidth plays a much lesser role in that. So this is the latency. Lower latency is helpful because there are some control messages, acknowledgements, retransmission requests. So they need to reach quickly. So latency plays a big role in such messages, in making them reach faster. And there is also what is called as intelligence in the network, meaning one option is that CPU copies the entire data in the buffer of the network interface card and then it goes. So the CPU has to work towards that. However, if there is offloading, what the CPU does is it will just give a pointer to the network interface card saying that, hey, at location 1000, 50 bytes of data is waiting for you. So what will the network interface card do? Go to this location, pick up 50 bytes, send it across. On the other side, those bytes are delivered in the memory. Well, who is doing that? The networking stack is doing that. As a result, host processor is now free to do computation. It doesn't have to worry, it doesn't have to spend time in doing network related things. So that is what the newer networks are doing, so that the CPU can concentrate only on computing. So now let's look at the HPC network. So aim here is to move data from memory of one node to node to the memory of another node. This I have already told you. So this can happen in various form, one to one. So point to point communication. That's one way. One to many. That means you want to distribute across to many. So that is called as broadcast. Many to one, meaning many nodes are sending data to one. So this is collect. So more about this you will understand tomorrow when we look at MPI. Okay. Now, how can you make it efficient? How can network contribute towards this? So for that you have intelligent hardware. Like I'll give you example of Paramnet, which CDAC has designed. So they offload the transport layer in the hardware. So what does this transport function do? Sequencing. This was explained to you by Amod. Reassembly, error control, using the best path, and event notification. So as I mentioned earlier, simply the CPU says that so much of byte, 1 MB of data is at this location. What is the packet size? Packet size is, let's say, 4 kilobytes. So make packets of 4 kilobytes, sequence them, then send them one by one. At the receiver end, rearrange them, reassemble them. If some packets were lost, resend them. Make sure that duplicates packet do not appear. All of this is taken care by the network. CPU doesn't have to do anything. So that is what is the trend that is being followed in HPC network. That if you use simple Ethernet, the CPU has to do all of this. The TCP protocol handles all of this. But however, HPC networks are confined to a small cluster. They are not like spreading across cities. In a room, there is a cluster of nodes and they are all connected through this high speed network. So that is how the system area network differs from a local area network. But it will take up all these functions which otherwise are to be done by the CPU. Then coming to the network topology, what is an ideal topology is that the network performance should not degrade with number of compute nodes. We said that scalability is an attribute of the topology. So typically there should be an independent path for messages between any pair. Okay, so now this is costly in the sense that if you want to have something like this, but this is, remember, we are talking about ideal. And latency should remain constant, that any number of nodes you add within one hop you should reach the destination. Okay, but in practice you have to make a compromise. Why? Because this is independent path for every message between any pair, means it's a fully connected topology and directly you can reach it. But then you can, if you design a network like this, it will be very costly, and every time you add a node you will have to add more number of links. So performance is getting, best performance is good, but you have to balance it with what practically it should be feasible and cost should not be exorbitant. So there are some of the popular networks. One of them is called as fat tree, which is also called as Clos network. So if you want to know more about Clos network, just search for it. It will tell you its attribute. It will also tell you the mathematics behind it, and but it is quite common for HPC network. So what happens in Clos network is number of levels that the switching takes place, that is limited. We are trying to reduce the hop count. Okay, so I will give you some diagrams in the slides to come. Okay, so typically what are the things that we need to build one? Okay, so here is an example which is the pictures that you see here. They belong to Paramnet. So this is a network interface card. This is a PCI interface, PCI, and on this side there is a link interface. So such card will go in every node. Every node will have one such card, and this is one switch. This was one leaf card. This leaf card has 8 port. There are 6 such, so 48 ports. So up to 48 nodes can be connected to this. I will tell you what you do when you go beyond 48 in the slides to come. So you need an NIC in every node and a switch which connects forms the cluster. Okay, what are the links? How does the cable go from here to here? It can be either copper or it could be fiber. Fiber goes longer distance, copper is few feet, few tens of feet. So now what you can use for HPC, it could be standard based like Ethernet, InfiniBand. So this is standard based or proprietary like Intel makes OmniPath, Cray makes Aries, CDAC has its ParamNet range, and Fujitsu use what is called as Tofu. Okay, so these are some of the commonly used networks. Now coming to the flat tree. So now you have in a flat tree, you have these are the links. So this is the node. So node 1, 2, 3, 4, 5, 6, 7, 8 nodes are here. So these are typically, these are the node compute node, you can say the lowest end. Now this is a level 1 switch. This is level 2 switch. This is level 3 switch. Like this you keep on going. So now just notice the thickness. Suppose this is 10 MB. So this is 10, this is 10, this has to be 20. This is 20, this is 20, this has to be 40. This is 40, this is 40, this has to be 80. So if you have like this, that a link becomes fatter as it goes up. This is ideal, 80, 40, 20. So they will have dedicated path because whatever is the low uh, upstream bandwidth is a summation of downstream bandwidths. Okay. So this typically gives best performance when used in non-blocking mode. So this is non-blocking. 20 plus 20, 40, 40 plus 40, 80. But in practice, this may not be so. 10 plus 10 may not be 20. It may be 15 here, 15 and 15. 15 and 15 may not be 30 here. It may be 25. 25 and 25 may not be 50 here. It may be 40. So this is called as blocking mode because not everybody is communicating to everybody all the time. Because that's why you get into what is called as blocking mode. Okay, so non-blocking mode is ideal, but that is very costly. Another thing is called as torus. If you can notice here, this is a three-dimensional torus. It's a blocking network because the bandwidth here, let's say if it's 10, then this also will be 10 and this also will be 10. So if 00 wants to send data to 02, it will go through this 10 Mbps. 01 wants to send data to 02, it will use the same 10 Mbps. So like this, though there is a redundant path, but now this is a 3, so it looks easy, but you can have 27 nodes or you can have like a power of 3 nodes. So this is a cost effective for large number of nodes. This is best performs good when used in non-blocking mode. It cannot be it cannot be in blocking mode. Okay, so it will give you a best performance then. Okay, so meaning that if you notice here, we had said that non-blocking is that it will have the bandwidths are going to be scaling up linearly and the total bandwidth of the downstream, if you add them together, you get the upstream bandwidth, but in practice, it's not so. Same case is here that it's non-blocking mode. Okay. So this will be useful when you have data locality, that is one is talking to 2 or one is talking to 0. If they are talking to neighbors, then it is good. The expansion is easier because you can keep adding nodes and then because it's a ring, so you don't, if it was something like switch or if it was like fully connected, then you would have required to upgrade the links. Here, what in a ring, it's a three-dimensional link. You just break it, add a node, break it, add a node. Simply, you can keep adding them. Obviously, it has a performance limitation because more the number of nodes in a ring, the communication is going to be more. But this is a topology that is 3D torus is what is accepted for local communication. This is very, very important. But if you want to have global communication, you use mixed topology. That is, you use factory for collective operations because they have to traverse, and torus is not good for collective communication. It's not good for broadcast communication. But localized data communication, torus is good. So in practice, one would use a switch and a torus. So remember, a torus does not need a switch. Torus, you just connect the NICs. Okay, but you need 2 ports or 6 ports on a network interface card. So how do you build HPC networks? The switches are available in small port count. They are called as edge switches, like 20, 32 port, 48 ports. Large port count, they are called as core switches. Okay. So for small
Excuse
clusters,
me, sir.
yeah,
Sir, I have a question. Can I go?
yeah,
Can I ask? Yes, sir.
yeah,
So
yeah.
can I go? Can you go to the previous slide? Yes, sir. So if we want to go from 00 to 12, how should we go?
Okay. So you are saying from 00 you wish to go to 12. Okay. So using this link, you will have to come here, and using this link, you will have to reach. Okay.
Sir, what about like 00 and so 00 to 02 and 02 to 12 will also be the same thing.
Correct. So there are multiple paths. Yes. So what happens is the functionality of switch, the routing part. So like if you go this, functionality of router or switch is built in the each of these nodes, because there are 3 paths to reach a destination in this case, rather
Yes.
6 paths in this case. It's a 2-dimensional, so 4 paths, sorry. You can have a 3-dimensional torus also, okay, in which case there will be 6 paths to reach any destination. So a ring is 1-dimensional torus. This is 2-dimensional, and now we have 3-dimensional. So so if you notice here again, if you take this as a node, you can go in x direction. This is x direction. Then there is a y direction and there is a z direction. So 3 directions are there to reach. But this is not 3D. Remember, this is only showing on 2 dimension. In the 3rd dimension, you will have one more layer of connectivity. Okay, so that is how it goes. So the switch is now is inside this. So please don't get confused. This is actually a 2D torus. Okay, a 3rd dimension will have. Imagine this as a plane. Okay, imagine this whole thing
Yes.
as a. Okay, so these are 2D planes. So this actually is a wrong thing. It's a typo. This should be 2-dimension. So imagine this as a plane, this 2D in a plane, and you have multiple such planes, and there is a connectivity between them. So that will be the 3rd dimension, and a ring like this. So that will become a 3rd dimension. That will make it 3D. Okay. So this functionality of switch and routing is built inside every node, NIC. You don't need a dedicated switch. But in this case, you are adding a layer of switch. Why? You want to make communication between broadcast and other one to be handled by the switch. Okay. Does this answer your question?
Yes, sir.
Okay. So now we are coming back. Torus and switch is one aspect. Now we were looking at another one, which is like this, which is made using only switches. Like this example that I gave you. If you want to build only purely switch-based network, a class network, then it will look like this. There are nodes which are the computers. So now this particular edge switch is a 32 port. So you divide it in 16 plus 16. Okay, so 16 go to individual nodes. So this, suppose each bandwidth is 100 Mbps. So you will have 1600 Mbps dedicated to the downstream and 1600 Mbps for upstream. Now this 1600 Mbps is divided into 800 plus 800. Okay. Now these are the core switches. So obviously these core switches will have more bandwidth, and they are capable of taking, if you notice here, 800 into 4. So there is nothing upstream, only downstream. So 3200 Mbps is this cumulative one here. Okay, and this one has got 1600 plus 1600, again 3200 Mbps only. So this is the way you will connect it, and in some cases you may even go for 3rd layer if the number of nodes increase. So now that is again a design criteria. I have kept a very simple network here with 48 nodes which are connected using 4 edge switches of 32 port and 2 core switches of 32 ports each. Okay, so that is how you would connect them. Okay, so this is again, we will not get into details of this because that itself again needs a detailed discussion. Okay. So before we end for break for lunch, I'll just compare SMP and cluster. So SMP management wise is easy because there is one box. Cluster, you need more effort. Some node will go down, something will happen, network will go down. So you need a cluster management tool. I will show you in the Sucheta will show us one cluster management tool in the afternoon. Okay. Power, it will take less power because one common power supply. Here you have distributed power supply and efficiency of that power supply comes into picture. So cluster will need, if you like, imagine that there is an 8 CPU cluster and an 8 node cluster. Okay, so obviously 8 node cluster will take more power, take more space because you have each individual box has motherboard, hard disk, all that. Scalability wise, cluster is good. Network just keep patching in more nodes. Your cluster scales up here. I mean, it's going to be costly because each SMP will have a limitation. Availability, in the sense that something goes down, then the whole cluster can go down, a part of it go down. In cluster, it is easy to build redundancy because each unit is autonomous. Price wise, cumulative price of 8 node cluster will be much lower than one 8 CPU SMP box. Okay. So that ends up, I tried to capture some attributes, important attributes of see, last week generic treatment of network was given. Here we looked at how we can adapt it to a, for an HPC kind of workloads.